Hello students, today we will discuss about basic and intermediate concepts of pipelining. So as you know, pipelining is a mechanism that is used with uniprocessor to increase the performance of especially the CPU present in a computer system. So when it comes to multiprocessor, we are having multiple processors available parallelly so that we can utilize those different processors and we can increase the speed of a CPU, means speed of a computer. But in the case of a uniprocessor system, we are having only one processor and most of the resources are single. So in order to provide parallelism on this single uniprocessor system, it is always better to use the concept called as pipelining, which was very popular in the earlier days of computers. So we will see some basics of the concept called as pipelining. Now let us see what is actually a pipeline. So it is actually an implementation technique whereby multiple instructions are overlapped in execution. So as you know, the computer execution or a program is being executed in a computer is actually consists of a number of instructions, thousands of instructions that are given to the system, and these instructions are executed one by one. So when it comes to pipelining, these multiple instructions of or that is given to a system will be overlapped because we are having only one processor and only few set of resources. So if we try to overlap these instructions in terms of times, that means without taking the entire time for the first instruction, then start the second instruction, then go for next instruction, what we can try to do on this pipelining is just overlap. Before completing the first instruction itself, we can start the second one. Similarly, before completing the second, we can start the third. So in order to arrange these instructions in some order, that is by giving an overlapping, we can increase the speed of the computer system. That means more instructions can be executed within a given limited time. So the basic idea of pipelining is to do overlapping on the various instructions that are submitted to the computer system. So we will see the exact figure and explanation on how this overlapping can be done in the following slides. Also, it takes the advantages of parallelism. So even if we are not having parallel resources available, the overlapping or the pipelining procedure will give an advantage of having parallelism within the computer system. The key implementation or it is the key implementation to make the CPU faster. So we are doing this pipelining on a particular machine only for increasing the speed of the processor present in that particular system, especially we are having only a single processor available. Now each step in a pipeline completes a part of an instruction. So the pipeline will be having a number of steps available, and each step of that particular pipeline completes a part of an instruction, as I was mentioning here. So if this is one step, that is one step of pipeline, a part of instruction will be executed. Now this is another step, another part of second instruction will be executed. Similarly, at the same time, the remaining part of first instruction will also be executed. Now when it comes to the third one, this part of instruction, this step will be executed. At the same time, the remaining of the second, remaining of the first will be executed. So in every step, so this is the first step, then we are having the second step, then we are having third step, up to the maximum depth, that is up to the total number of instructions available within the system. This procedure will be continued so that we can reduce the total time taken for the execution of the set of instructions that are submitted to the computer. Now each of these steps present, so this is the first step, this is the second step, this is the third step. Each of these steps can be considered or can be called as a pipe stage, or it is sometimes also called as pipe segment. So this is one instruction, second instruction, third instruction. So every instruction will be going through some stages. So first stage, what is the status? Now second stage, what is the status on all these instructions? Third stage, what is the status of all these instructions? Then fourth stage, what is the status of all the instruction? So automatically we can clearly understand that means initially only the first instruction will be in the pipe stage, but from the next cycle, next clock cycle or next time, so here we are actually considering the clock cycle of a computer system for performing the different stages of this pipelining mechanism. So we have to consider some time, because based on the time only we can understand that the time reduction, or we can see the speed increase of a computer system. So now the different stages are there. After that, the stages are connected one to the next to form a pipe. The stages are connected one to the next to form a pipe. Just like imagine a building construction is happening. What is happening? So if somebody is trying to bring some mixed cement, so some people will be standing in between. So this is slightly far away. So what this person will be doing? This person will be mixing that cement, and he will be handing over that to the next person, and he will be handing overing that cement will be into a different person, and this he will be handing over to the person who is actually building the home. So this is the cement that boats, and first after this person A handing overing that into this person is free now. Now he can take another cement boats. Then after handing overing this cement boats by this person, that is B, to the next person, this person is also free. So he can collect the previous one from this person to this person. So what we are doing? We are doing several operations, several tasks by A, B and C and D. So at any time every persons are actually busy. Similarly, every instruction, some portion will be executed at any given time. So at 2 o'clock this person is constructing, this person is giving the cement pack, this person is also giving the cement pack, this person is mixing the cement and handing over that to the next person. So at any time these persons are actually busy. So similarly we are also applying the same concept into the different instructions that is submitted to the computer system. So this is only an analogy example. We will see the real happening with the computer instructions that are given for execution. So we will be having different stages, and these stages are connected to form different, or we can call it as a pipe. Instructions enter at one end. At one end the instruction enter, then progress through different stages. So it will be like instructions will be progressing through different stages. So we'll be having different stages. Every stages will be having some status of each of the instruction, and exit at the other end. So almost the diagram will be in this format. So instruction arrives here, So this is one instruction. Next instruction, whatever it be, different instructions arrives at one end. Then on different times, different portion of those instructions will be executed in different stages, and it will be exiting at the other end of the entire pipelining architecture. Now the advantage, the throughput of an instruction pipeline is determined by how often an instruction exits the pipeline. So this is the pipeline, different instructions are executed in parallel, and how often an instruction exits. So the completion of the execution of different instruction, that means one instruction come out, then second, third, fourth, fifth, etc., etc. The different instructions are actually coming out of the system, and this number of instructions that are coming out of the pipeline will actually decide the throughput of the instruction pipeline. Because if more instructions come out within less time, we can say that this instruction pipeline is having a higher throughput. Okay, as all stages proceed at the same time, the length of a processor cycle is determined by the time required for the slowest pipe stage. So after the starting of the first instruction, then comes a number of other instructions, and different portions of those instructions are executed in parallel. The same time, what is happening is it is actually passing through different processor cycle. Now after some time, we can see that all the instructions are executing, or some portion of all the instructions are executing at the same time. So the total time required, means the length of the processor cycle is actually determined by the time required for the slowest pipe stage. So whichever stage is having the slowest operation, that will decide the length of the processor cycle. Now if the stages are perfectly balanced, means all the stages are almost taking exactly the same time, then the time per instruction on the pipeline processor is equal to, if all the stages are balanced, means almost all the stages are taking the exact same time, we can decide the time per instruction on this pipelined processor by using the following formula, that is the time per instruction on unpipelined machine. So here we are actually going to compare two categories of machine so that we can decide whether the pipelined processor is better than the unpipelined processor. So the time per instruction on unpipelined machine. So assume that an instruction on unpipelined machine takes 5 seconds to finish the task. For example, it will be divided by number of pipe stages. That is, if the number of pipe stages are 5. So what is the value here? 5 by 5, that is 1. Now we can say that one clock cycle will actually the time taken for, or the time per instruction on a pipelined processor. So normally if the different instructions are executed separately one after another, it will take 5 seconds. That is this one. But if you are having a pipelining architecture with 5 stages, and if you do this calculation, time per instruction on unpipelined machine as 5 to the number of pipe stages. So we are going to implement the same on a pipeline architecture with 5 stages available. Now we are getting a value 1 that decides the time per instruction. So for the completion of an entire instruction, it will take only 1 clock cycle. So this is only an example just for getting an idea regarding and means a change from an unpipelined machine to the pipeline machine. Now pipelining yields a reduction in the average execution time. That is always clear. So for example, if a car is given to a workshop and it is having some complaints, and assume that it is having 4 complaints. Now after the completion of first complaint, means that is being corrected, then means first complaint will be rectified by the first mechanic, and after the completion, if it is given to a second mechanic for the next complaint correction, then after that is given, after the completion of that correction, it is given to some other person. So if it is going in that way, automatically it will take more time to complete the entire repair of a car. But if it is being done in parallel, that means if the first person is doing some part of the correction, then in the same time, if some other part can also be executed in parallel by some other mechanic, so that we can increase the speed of the entire procedure. That means the entire completion of repairing that particular car. Okay, so we can take several real-time example of pipelining in terms of what you say, the speed up of some task, several tasks to be completed. Means if you are using pipelining concept, it will be reduced, the time taken for the entire task to be completed will be reduced. And if you are not using pipelining mechanism, then the total time taken for completing the entire task will be more. Now we are actually reducing the average execution time per instruction. Now the reduction can be viewed as decreasing the number of clock cycles per instruction. So the number of clock cycles required for a particular instruction will be reduced if we are increasing the pipelining, or if we are using the pipelining concept, and accordingly we are actually decreasing the number of clock cycles per instruction. So how it will happen, we will see in the remaining portions. Okay, now pipelining is an implementation technique that exploits parallelism. That is only a recap among the instructions in a sequential instruction stream. So if you are having some set of sequential instruction stream available, it is an implementation technique, that is pipelining is an implementation technique that exploits parallelism. So if you are having some 100 instructions to be executed one by one, if we implement parallelism, means pipelining, it will exploit parallelism on these 100 instructions. So 100 instruction, if 100 instructions are executed separately one after another, if it takes 1 second for one instruction, totally it will take 100 seconds. But if it is given into a pipeline system, the time can be reduced a lot. Maybe within 1 or 2 or 3 or 4 or 5 seconds we can complete the entire set of instructions within that limited time. Now we will see the basics of a RISC instruction set that implements the pipelining mechanism. So we are considering reduced instruction set computer architecture, and we are considering one microprocessor which is called as MIPS, which was already discussed in the previous session, and we are considering only one particular processor, that is the MIPS microprocessor, and which is based on the RISC architecture. It is having only some reduced set of instruction set architecture only. Now before moving into the usage of this instruction and how this pipelining can be implemented on this RISC architecture, we will see the various characteristics of the RISC architecture. First thing is, all the operations on data apply to data, or the data will be applied to only registers, and we are actually trying to change the register. So operations will be applied mostly on registers, and we are actually trying to change the register content. So that is the feature of a normal RISC based architecture. So most of the operations are related to registers. That is the point we are going to mention here. And the only operation that affect the memory, so most of the operations are dealing with registers and changing the register content, and the only operations that affect the memory are load and store instruction. So when we are using load and store instruction, load is used for loading from memory, that is for taking the data from memory to register, and store is used for moving the data from memory from register to memory. Okay, so movement between memory and register is actually done by using load and store instruction. So if you require some data as input, we are using load, that is taken from the memory. If you want to store the result into the memory after the completion of execution, so we are moving the register content. The result is actually present in the register, and if you want to move that into the memory, we are using the store operation. So only when we require load and store, only when we are using load and store instruction, we need to have a reference to the memory, but other time we are only focusing on registers. The instruction formats are a few in number. That is another feature of RISC-based architecture. We are not having much instruction formats available with these RISC architectures, especially with MIPS, and most of the instructions are having the same size. So you might have we have already mentioned about MIPS. MIPS for encoding mechanism. It is having a fixed size format, encoding format available. So most of the instructions present in this MIPS architecture is having a fixed size, so that we can easily implement the concept of pipelining. Now a MIPS instruction set provides totally 32 registers. It consists of 32 different registers, and the different classes of instructions present in the MIPS architectures are ALU based instructions. It consists of register contents, between register operations, or between register and some immediate value. So between registers or between register and immediate value, it will be having some operation and store the result into a different register. That is ALU instruction. Then it is having load and store instructions. As I was mentioning before, it takes a register source called the base register. That is one of the operation with this load and store. Then it will take an immediate value which is called as offset. That is taken as the operand. So base register will be added with offset and will form the effective address that is used for a particular memory reference. So that is the operation happens with load and store. So here for load and store also we are actually referring a register that is for getting the base address, and it will be added with the offset for finding the exact memory address where the data is actually presenting or where the data to be stored. Then the third class of instruction is branches and jumps. So we are actually doing this branch on many RISC architecture in two different ways, either with a set of condition bits or condition codes. So based on the value, condition means the value present in a particular register, or a set of condition bits are used for having comparison, means based on that value, particular value, we are doing branching or jumping from one location to another location. Or between comparison between a pair of registers, we will have some comparison, we will compare two register, and based on comparison of register values, register A is compared with register B, or between register and a 0, means if the register is having a value greater than 0, or if the register is having a value less than 0, etc. In all these categories we can have a condition comparison, and accordingly we can have a branch or jump operation. that is movement from one address to another memory address. Now we will see a simple implementation of a RISC instruction set. Now initially we are considering what are the different contents of a particular instruction present in the MIPS architecture. So we are initially considering the implementation without using a pipelining. If you are not having pipelining, how the instructions will be executed. Now every instruction takes at most 5 clock cycles. So we are considering in general. So if you are having one complete instruction available, how many clock cycle it will take? So we are having almost 5 clock cycles present in a particular instruction. Okay, so this is the first clock cycle, second clock cycle, third clock cycle, fourth clock cycle, and fifth clock cycle. It's like time. For example, first second, third second, fourth second, 5 seconds. So totally 5 seconds are there. Now clock cycle is like it's a time dimension. Okay, so in computer we are calling it as clock cycles. So in the first cycle, second cycle what will happen, third cycle what will happen, fourth cycle what will happen, fifth cycle what will happen. So first cycle, so every instruction is divided into 5 different cycles. So each instruction in the first cycle something will happen, second cycle, third cycle, fourth cycle, fifth cycle something will happen. So let us see what are those different 5 clock cycle operations. So first operation, so most of these 5 not all the instructions follows these 5 clock cycles, or they are not following these operations on different 5 cycles. Some of the instructions requires only 2 clock cycles, some of the instruction requires only 4 clock cycles, and some of the instruction requires 5 clock cycles. So 5 is common, that is why it is given as 5 different clock cycles. So all the instruction, the first step will be instruction fetch cycle. In the first cycle it will do instruction fetch. Instruction fetch means it is reading the instruction from the memory. So some instruction is given, submitted to the system. So in order to execute that instruction, it will read the instruction that is submitted from the memory. So reading the instruction, that is called as instruction fetch. Then after fetching the instruction, it will go to the next stage. Second stage, what is happening is instruction decode and instruction fetch. Instruction decode or instruction fetch, they are taken, it is given together. It is done in parallel with reading the register. So instruction decode, the meaning is it will understand what is that instruction, understanding the instruction. And so read the instruction and understand the instruction. That will happen with instruction decode. So instruction fetch, the instruction is collected from the memory. Then after the collection, it will understand what is that instruction and it will read the content of that register. That is called as instruction decode or instruction or register fetch cycle. So it will happen with the second cycle. Then it will move to the third cycle. What is happening with the third cycle? It is the major portion where the actual execution happens. So this is called as execution cycle. So some ALU execution will be happening, or it will be doing some effective address calculation to find out a memory location where the data to be stored. So the execution portion, the third cycle, actually consists of 3 different functions. One is memory reference, where we are calculating effective address by using the base address and the offset. Then second operation is the operation between register and register ALU instruction. Some arithmetic manipulation will be happening, or sometimes it will be having some operation with the register content and an immediate value, and will perform some additional or subtraction or similar operations. So third cycle, so during the first cycle, instruction fetch, then decode, then execute. Then in the fourth cycle, it will have the memory access. So if the execution, if this ALU execution requires some data to be taken from the memory, it will go for the next step, that is memory access. So not all the instruction requires memory access. So whenever it requires some data from memory, it is it is going into the fourth clock cycle, that is called as memory access. If it requires some data from memory, then only it will go for memory access. Then if it is not, that instruction does not require that clock cycle operation. Now after that it will go to another fifth clock cycle, which is actually doing the result storing operation, that is called as write back, generally called as WB. It will write the result into the register file. So after the completion of all these operations, the result to be stored in to the register. Okay, so whether it comes from the memory or from ALU, wherever it is. So if sometimes we need to store the result from memory, or from ALU, some ALU operation, whatever it be, finally we need to write the result. So sometimes when we are reading the data from register, reading the data from memory using load operation, that data to be written into the register, or after the completion of these operations we need to write the result into the register. So result to be written back to the register. That is happening with the write back clock cycle. So every RISC based architecture, or when you take particular MIPS concept, we are actually using a maximum of 5 clock cycles that consist of instruction fetch, instruction decode, execute, then memory and write back operation. So that is, so a single instruction consists of 5 different clock cycles. So in order to explain this pipelining concept, we are actually following these 5 stages or 5 clock cycle stages, and how these stages can be executed in parallel by using pipelining mechanism. So 5-stage RISC pipeline of MIPS processor. So 5-stage RISC architecture, or sometimes it will be asked like 5-tier RISC architecture, or sometimes it will be asked like 5-layer RISC architecture. So this is actually by implementing the pipelining mechanism. The pipeline is actually maintained in a MIPS processor by using these 5 stages. So 5-stage RISC pipeline architecture of MIPS processor is given below. So this is the basic of pipeline concept. So we can pipeline the execution by simply starting a new instruction on each clock cycle. Okay, so just look at this example. Now in the Y axis, or this side, what is given is the instruction number. So this is the first instruction, instruction I. This is next instruction, instruction I plus 1, I plus 2, next instruction I plus 3, I plus 4. So totally here we are having 5 instructions, one after another comes. Okay, now here in the H side, what we can see is the clock number or clock cycles. So this is the first clock cycle, second clock cycle, third cycle, fourth cycle, fifth cycle, sixth, seventh, eighth, ninth. It will go in this way. If you are having more instructions available, so time will be always increasing. The clock cycle, the 10th cycle, 11th cycle, 100th cycle, 1000th cycle. So cycle will be incrementing always. So time, so as we are moving ahead, the time is actually increasing. So now if it is 7, after some time the time will be 8, then after some time the time will be 9. So in each of these time, what is happening? So in that way we are mentioning this pipelining mechanism. So what is happening is first stage, what is happening, just have a look at here. instruction I arrives, it will go for instruction fetch. So that time no instructions are currently available. Now in the first clock cycle, instruction I will perform instruction fetch, then it will go for instruction decode. In the second clock cycle, it will go for instruction decode. In the same clock cycle, the next instruction arrives and it will go for instruction fetch. So in the second clock cycle, two operations are happening: the instruction decode of the instruction I and instruction fetch of the instruction I plus 1. Why? Because instruction fetch happens with the memory, instruction decoding is happening with the register. Okay, so these are two different resources. So the second instruction cannot start from the first clock cycle, because in the first clock cycle some other instruction is actually doing instruction fetch. In same time, no other instruction can do instruction fetch. Okay, so what we are considering here is we are having two memories actually. So this instruction fetch is dealing with instruction memory, and this memory data, for accessing data we are using a separate data. So we are assuming in that way. It is not always possible, but most of the systems, they are having two different cache memories for accessing two different categories of memory. So one cache memory is deputed for instruction for getting the instruction, and one cache memory is deputed for getting the data. So instruction fetch happens with the communication of instruction memory, and this memory, data memory access, will be happening with the communication with the data memory. So we are assuming that we are having two different cache memories are available. Okay, so in the next clock cycle, in the third clock cycle, the instruction I will go for instruction execute. In the same time, I plus 1 instruction will go for instruction decode. In the same time, I plus 2 instruction arrives and it will go for instruction fetch. So 3 clock cycles over, and parallelly 3 instructions are under execution. They are partially being executed. Now the first ith instruction will go to the fourth clock cycle. It will have the memory access, data memory. In the same time, I plus 1 instruction will go for EH stage, I plus 2 instruction will go for instruction decode, and I plus 3, a new instruction will arrive and it will go for instruction fetch. Now in the fourth clock cycle, 4 instructions are executing in parallel. Some portion of those instructions: instruction I memory access, instruction I plus 1 execution, instruction I plus 2 instruction decode, instruction I plus 3 instruction fetch. Now when it moves to the fifth clock cycle, instruction I will go for a write back, writing the result. The same time, I plus 1 go for memory access, I plus 2 will go for execution, I plus 3 will go for instruction decode, and I plus 4, a new instruction arrives and will do instruction fetch. Now we can see in the fifth clock stage, in the same clock number, in the same clock cycle, that is within the same time, 5 instructions are executing in parallel. That means some portions of each of the instructions are executed in parallel. So after write back, instruction I finishes. Now in the sixth clock cycle, instruction I does not require any more operation, so it is not doing anything. Then instruction I plus 1 will write the result. Same time, I plus 2 will write memory. Then I plus 3 will do execution, and I plus 4 will do instruction decode. Then in the seventh clock cycle, I plus 1 is already over, so it will not do anything. Then instruction I plus 2 will do write back. Then I plus 3 will do memory, and I plus 4 will do execution. Then in the next clock cycle, 8th, I plus 2 is already over, I plus 3 will do write back, and I plus 4 will do memory. In the next stage, that is 9th clock cycle, I plus 3 is already over, and I plus 4 will do write back. Now the 5 different insertions are already being completed. Okay, so we can directly understand how it can improve parallelism. Okay, so just assume totally for the completion of 5 different insertions, it took total 9 clock cycles. It took totally 9 clock cycles. So you can just imagine this 9 clock cycle as 9 seconds. Okay, normally the clock cycle is evaluated like it is given like 1 nanosecond. That is considered as 1 clock cycle. Okay, but whatever it be, we can take any dimension for just for understanding. So 9 clock cycles are taken for the completion of 5 instruction. Okay, now just assume that if we are not implementing pipelining over here, what will happen? Instruction I will take 5 clock cycle. Then after that instruction I plus 1 arise, it will take 5 more clock cycle. Then instruction I plus 2 arise, it will take 5 more clock cycle. Then I plus 3 arrives, it will take 5 more clock cycle. Again I plus 4, it will take 5 more clock cycles. So totally for an unpipelined processor, if the system need to execute 5 different instructions, it will take 5 plus 5, 10, 15, 20, 25 clock cycles for the completion of these 5 instructions. But when we implemented pipelining, this entire 5 instructions were completed within 9 clock cycle. Okay, 9 and 25. So what we are actually gaining, we are actually increasing the speed of the entire execution. So a task which actually required 25 clock cycle was completed within only 9 clock cycle. I hope it is very clear. It is a very simple format, so it is a very important portion. 5 stages of risk-based pipeline of a particular, here it is taken MIPS architecture. Most of the systems are actually following the same pattern only, but we are considering specifically MIPS. Okay, so just remember these 5 different operations that can be part of a particular instruction and how the different operations of different instructions can be executed in parallel. Okay, so now finally you can see one more thing in the center portion. In the 5th clock cycle, we can see that it is doing all the operations simultaneously. Means instruction fetch of one instruction, instruction decode, execution, memory, and write back. So all these 5 instructions, that is part of a single instruction. But now in the 5th clock cycle, the same set of operations of different instructions are executed within that single clock cycle. So on an average, if you are having some thousands of instructions available, it will take some 4 clock cycle for the initial period, and from the 5th clock cycle onwards, it will take only 1 clock cycle to complete an entire instruction. So what was our initial imagination? One instruction takes 5 clock cycle. That is our initial assumption normally. But when we implement pipelining from the 5th cycle onwards, we can see that the entire these are the instructions, means these are the operations required for a particular instruction. So all the operations are executed within that single clock cycle. So on an average, for a pipelined machine, the average execution time for a particular instruction is only 1 clock cycle, so that we can reduce the time taken for the completion of a number of instructions by increasing parallelism in the form of pipelining mechanism. I hope it is clear. It's a very simple concept only, but very useful one. So these are the further explanation on the same thing. Each of the clock cycles from the previous section becomes a pipe stage. Each of the clock cycle from the previous section becomes a pipe stage. Okay, so you can just look at the previous thing. Each of the clock cycle, so first clock cycle will form, it will form a next stage, then it will form the next stage, then it will form the next stage. In that way it is. So how many stages are there? First, second, third, fourth, and 5 stages are there to form a pipeline. So insertions arrives at one end, as I was mentioning before, and insertion exit at the other end by forming a pipeline here. So we are having different pipe stages available. This is from first stage to second stage, third stage, fourth stage, fifth stage. So we are having totally 5 stages available in this particular pipeline architecture. Although each insertion takes 5 clock cycles to complete, during each clock cycle the hardware will initiate a new insertion and will be executing some part of the 5 different insertions that I have already explained. We use separate insertion and data memories. That was also mentioned. For insertion fetch we are using insertion memory, which is a cache, and for data access we are using data memory, which is also a cache. So we are having different cache memories away. So the usage of multiple caches will give an added advantage to the pipelining mechanism. The use of separate caches eliminates the conflict for a single memory that would arise between insertion fetch and data memory. So if we could have only one memory, the problem was that if insertion fetch and memory access to be done at the same clock cycle will become a difficult task. Then the register file is used in 2 stages. So previous one we are mentioning about memory. The register file is used in 2 stages. One for reading the register content, that is in the insertion decode stage, and second one is for writing the final result, that is write back stage. Now to handle reads and write to the same register, we perform register write. So okay, so we can look into the previous diagram once again. So one more problem is there, how we can handle that problem with a pipeline architecture. In this diagram we can see that insertion decode. So in this particular 5th clock cycle we will see we are using write back and insertion decode at the same clock cycle. Write back, and so here also we are using write back and insertion decode in the same clock cycle. So write back uses a register, and insertion decode also uses a register. So this is actually register file which is a common area for reference to each register. So each register details are actually taken from register file. So both are actually, so write back referring to the register file and insertion decode is also referring to the same register file. So this is a single resource, so these two cannot be done at the same time. So we are actually doing a solution for that. So this is the register, we are going to access this register. So this is a particular clock cycle, 5th clock cycle. Okay, so this is one entire clock cycle. So what we are doing is we are dividing that cycle into 2 different cycles, means partial cycles. This is the half cycle and this is the remaining half cycle. So we are actually dividing the time into 2 different half cycles. One cycle will be divided into 2 half cycles, and in the first half all the writes will be happening. So it is reserved in that format. In the first half only register write will happen of the same cycle, and in the second half the register read will happen. So this write back will be having priority on this, on a part if these 2 operations arrives at the same time. A write back in the first half of the same cycle, this writing will happen, and in the second cycle this insertion decode. So here write back first will happen, then here in the second cycle insertion decode, that is reading will be happening. That is a solution we are using when we are performing access to the register file at the same time. So we will see the structure, how it can be really implemented by using all these devices. The same thing is given in a different figure here. Now this is the program execution order that is happening in the y-axis. Program execution order is happening, and this is the clock cycle. Clock cycle is given here. This is clock cycle. This is clock cycle 1, clock cycle 2, 3, 4, 5, 6, 7, 8, 9. Clock cycle. The same thing only. Now this is insertion memory. So now the operations are converted into the corresponding resources, the device that is used for performing that task. So this is the insertion memory. Now this is a register file. Then register file, in the second stage it is used for reading the register content, that is insertion decode. So you can see that in the first portion, half of the portion is given dotted lines, and right hand side it is given bold lines. So that indicates the division of that register into two different cycles. It is divided into two parts. In the same clock cycle it is having two parts. One portion is for writing. So insertion decode is not doing writing, it is doing reading. That is why right side is given bold line. Then that is given to ALU. This is the execution place. ALU is the place where we do execution, happens in the third clock cycle. Then for data memory access, it is referring to the data memory. So insertion memory is there, data memory is there. Then finally after getting the result will be stored into register again. Now here you can see again we are having division of this register. Here first half is given bold because we are going to write the result, and second half is given dotted line because here there is no read happens. So for all the register, first half is dedicated for only writing and second half is dedicated to only reading. Okay, so in the same time, second clock cycle, second insertion arrives, insertion memory, here again register. So for the insertion decode session register, first portion will be always dotted line because it is not doing any write, it is doing only read operation. So in the clock cycle 6, again register writing will be happening, that is the result writing, and the same thing will go on in different stages. So this is the exact pictorial representation in terms of the resources used for all the operations of for all these 5 stages, like insertion fetch uses insertion memory, insertion decode we use register, insertion means execution we are using ALU, memory access we are using data memory, and for write back we are using register. Okay, so for memory there is no conflict because we are having separate caches, one for insertion memory and one for data memory. But for register we are not having different register files available, we are having only one register file which is the common. So in that, for reading and writing we are dividing the same clock cycle into two, half we are dividing into two, and we are performing read and write accordingly. I hope it is clear. Now the previous figure that we were mentioning now, it does not consist of the PC concept, that is a program counter. Program counter is the major element that decides what insertion to be executed next. So during insertion fetch phase itself, the next means the PC program counter value to be modified, because one insertion is being fetched automatically, the PC to be incremented by 4 to get the next address, the address of the next insertion. So to start a new instruction every clock, we must increment and store the PC every clock, and this must be done during the instruction fetch stage in preparation for the next instruction. So it is not specifically mentioned in the previous diagram. And also we must ensure that instructions in different stages of the pipeline do not interfere with one another. So we have already given this diagram almost in a pipeline manner, but it will not always execute in the same manner, because sometimes due to some delay in time of some operation there will be some conflict that may also happens, but we must be very careful about those problems, and it should not interfere with one another present in that particular computer system. So this separation is done by introducing pipeline registers. So one stage should not interfere with the second stage. So we should have a barrier. So what we are doing, so if we enter into a company or if we enter into a shopping mall, we cannot simply enter into that. There will be an intermediate present there. So he'll be asking, so that like a security person, he'll be asking the details, and accordingly we can enter into the company or whatever it be. So similarly, after the completion of each stage, we are actually maintaining a separate hardware portion that is called as a separate pipeline registers are being maintained, that is to be placed between two different stages, so that after the completion of one stage, whether it should go into the next stage or not, that decision will be made by the pipeline registers. So you'll see the formation of pipeline register in the next slide. So we are going to include one more hardware portion into the entire pipeline architecture, that is a set of pipeline registers are being included. Okay, so we are actually trying to increase the speed of computer system by implementing pipelining, but for implementing pipelining we are doing some extra hardware to be added and something to be done additional. So the cost will be increased automatically, but still our aim is to increase the speed of the system. So we are introducing a pipeline register between all the stages. So we require a number of pipeline registers between all the stages, and at the end of a clock cycle, all the results from a given stages are stored into a register. So that is the intermediate pipeline register, and he will be forwarding that to the next stage, that is on the next clock cycle. So next diagram will actually demonstrate that concept. The same thing, only thing is one hardware is placed in between two stages. So here also you can see pipeline registers are there. In the next stage also we can see pipeline stages. So what is the duty of these pipeline registers? These are additional hardwares placed between two different stages, from this stage to this stage. So instruction memory, it will read the instruction, and this register will decide whether it can go to the next stage. Then after the instruction decode, the result will be referred to the next register, and he will decide whether it can go for ALU operation. And after the ALU operation, it is given to this register, and he can decide whether it can go for data memory. And after that, it can decide whether it can go to the this register can decide whether it can go to or write into the register. So we are actually, in order to improve the performance, in order to have a security on all these interaction between different stages of pipeline, we are introducing a new hardware architecture that is called as pipeline registers. So as we can see, the different instruction, different stages, we require different registers. It will automatically increase the cost of the entire system that uses pipeline. So this is an example pipeline that shows pipeline registers between the successive pipeline stages. Here also you can see from data memory to ALU, we are having a feedback also, because if ALU requires some data from memory, it will communicate with that, and this will be given back to ALU. So accordingly this data will be executed on this particular clock cycle. So there will be a feedback here, and in every stage we are having a feedback given from register to ALU, ALU to data memory, and these three stages we are having feedback also, that is to be communicated from one stage to next stage, and from that stage to the previous stage also. So these are the basics of pipelining. What is pipelining, why it is being used, how pipelining can be implemented, what are the different stages of pipelining, and how we can improve the performance of processor with the support of pipelining, and also by including an additional hardware called as pipeline registers. So that is all about basics of pipelining and how it is being implemented. Now in the next session, next video, we will see about the different problems related to the pipelining, and how we can resolve the problems related to the pipelining mechanism. So that's it for now. Thank you.